So we've talked about the periodic table, and this is what you've seen, and this is what you'll continue to get on all the different exams. And in the last few chapters, we talked about several aspects of the periodic table. We're going to really focus in on this mass number right there. I just circled iron's mass number. That is going to be a very important part of the periodic table this week. Now, before, we called that the weighted average mass. And if I asked you for the mass of an average iron isotope, for iron, you'd say, oh, it's 55.845, and the units you would have used would have been AMU for atomic mass units. Well, this is a really good unit for single atoms or molecules. When you have something really, really small and you need the mass of just that one thing, atomic mass units are great. But there's no scale, no balance in the world where you can put particles on it and it's going to measure atomic mass units. It's just too small of a unit to be useful. Because in the real world, we like to have grams. Grams of something or something we can see, we can weigh, we can measure, we can use. So this number we're going to talk about takes on a new meaning. It is definitely still AMU, but we're going to talk about this in units of grams per mole. This is where we are changing it this chapter. And it's still the same number, but we're going to use that number as how much mass, in this case iron, would have if we had a mole of iron. Now, a mole is a quantity. This is a quantity like a dozen. And we would know that if we had this quantity, 1 mole, then we would have 55.845 grams of iron. And you can see that the mass of each element is different. So the same quantity of each element will have a different number of grams, a different mass. So that's the basis of this chapter. And again, it's the same idea as atomic mass units. We're just using them on a scale that's more applicable to real life and laboratory environments. Okay, so that number is called the molar mass. And that molar mass, again, is the grams of mass you'll have when you have 1 mole of a given substance. So if we look at silver here, if we had 1 mole, and MOL is abbreviation of mole, MOL is abbreviation of MOLE, by the way. So if we had 1 mole of silver atoms, it would weigh 107.9 grams. If we had 1 mole of carbon atoms, it would only weigh 12.01 grams because carbon is a lot lighter than silver. So this mole, this quantity, is right there. That's what a mole is. And that mole quantity is given the name Avogadro's number. Now, if I said you had a dozen of something, you would say you had 12 of those things. So I said you have a dozen donuts, you'd say I have 12 donuts. If I said you had 2 dozen donuts, you'd say I'd have 24 donuts. If I said you had 2 dozen eggs, you'd say, well, wait a minute, you can't use dozen with eggs. You just used it with donuts, right? No, that doesn't make sense. You could use a dozen with anything you want, right? Well, it's the same with moles. So if a dozen is 12, we would say 1 mole is a huge number. It happens to be 6.022 times 10 to the 23. This is a gigantic number, way more than a dozen. But it can apply to anything. I can have a mole of hydrogen atoms. I can have a mole of satellite dishes. I could have a mole of donuts. It doesn't matter. It's just a quantity. But the idea is when we have a mole of any of these elements, we know what the mass will be. Now we're going to use that quite a bit. Okay, so we said a mole is this number and is just like a dozen, just like 12 equals a dozen. So let's just put this in perspective. If I said you had 275,000 eggs, how many dozen eggs would that be? You'd say, oh, well, okay, I would just divide 275,000 by 12, and that's how many dozens I'd have. So now that you probably could do that in your head, let me show you how dimensional analysis would start to be used, because it's easy now. It'll probably get a little more complicated when we use chemicals. But the idea would be is that we'd have some information that we're given, a quantity of eggs, and we're going to say, all right, I don't want my number of eggs. I want to know how many dozen I have. So if I had 1 dozen of something, I would have 12 of those things. In this case, if I have a dozen eggs, I would have 12 eggs. And so dimensional analysis shows you what you probably already knew. You divide 275,000 by 12, you'll get your answer. Eggs cancel out, your units will be dozen eggs. So just to, not that this answer is going to win me a Nobel Peace Prize, let's just see what it is though. 22917. Now, I'm not worried about significant figures a whole bunch, because I don't know if someone actually counted these and it's the exact number. There's exactly 12 in a dozen, so that will not affect sig figs. But anyway, that's not what this is about. This is just the idea that we're converting eggs to dozen. All right, well, what if we wanted to convert it to moles? Well, we'd say, all right, well, we had 275,000 eggs. Now I need to convert eggs to moles. So if I have 1 mole of something, I have 6.022 times 10 to the 23rd of that thing. So if I had 1 mole of eggs, I would have Avogadro's number of eggs. So eggs would cancel out. My units left are moles of eggs. And this is where I highly recommend that you use your calculator, because we're going to be entering a lot of exponential notation, and it's always good to make sure that you guys are getting the same answers that I do. 4.57 times 10 to the negative 19 moles of eggs. All right, so assuming that entering the exponential or scientific notation in your calculator is not a big deal, that's a pretty straightforward calculation. But of course, we don't talk about eggs in chemistry. You might in biology, but you won't have moles of eggs. You just have eggs. But we talk about things like iron atoms in chemistry. Now, when we talk about atoms, you're going to see why we need such a big number like moles, like Avogadro's number for moles. Because in this example, we have 5.25 times 10 to the 24th power of iron atoms. And if we wrote that out, that's what it would look like. So that's why we don't use regular notation, we use scientific. But anyway, if we had this many iron atoms, how many moles of iron atoms would you have? So you'd say to yourself, okay, I'm given the information that I have 5.25 times 10 to the 24th iron, which is Fe, atoms. How many moles of iron atoms would we have? All right, well, when we have 1 mole of anything, we have Avogadro's number of that thing. Just like 12 for a dozen, 6.022 times 10 to the 23 per mole. So if we have 1 mole of iron atoms, we'd have this many iron atoms. So iron atoms cancels out. My units will be moles of iron atoms. And again, it's good practice to divide this number by this number on your calculator to make sure you are entering the notation properly. All right, I got just plain old 8.72 mole of Fe atoms. All right, so that's the tip of the iceberg. We're just scratching the surface. But before we get into any more details, unless there's questions about that, let's get an idea of how large a quantity Avogadro's number is. So of course, anytime you describe something, a large quantity, you compare it to grains of rice. So you say, all right, how many grains of rice do you think would be in a bowl of rice? Just think about it. And you'd say, are there 1 million grains of rice, tens of thousands of grains of rice? Well, don't worry about a bowl of rice. Let's think about all the rice that was harvested in the United States in one crop season. All these little grains of rice. Do you think that would be a mole? Well, don't answer that question. What about all the rice that was harvested in the world in 1 year? Do you think that would be a mole? Would that be 6.02 times 10 to the 23rd grains of rice? No, it wouldn't be. So let me say this. This number is so big that in the history of the cultivation of rice, there has not been this many grains of rice produced in the world yet. That's how big this number is. So that's every crop of rice that's ever been harvested throughout human history. There has not been a mole of grains of rice yet. That is how giant this number is, to put it in perspective. But let me not end there. If you had a mole of marbles and you covered the earth with a mole of marbles, even the depths of the ocean, even the Marianas Trench, we'd be buried 3 miles deep in marbles. Okay, well, what about if we had a mole, Avogadro's number, of $100 bills? If we made a stack of $100 bills, it would be so tall that it would reach from the sun to Pluto and back 7.5 million times. And if you took a flashlight and you stood at the bottom of that stack of bills and shined the light to the top, at the speed of light, it would take 9,500 years for that light to reach the bottom of your stack of $100 bills to the top, if you had a mole of them. That is how big a mole is. So when we talk about a question like this and we say we have this many iron particles, you're like, all right, now I get why we need a quantity like a mole, because if we had this many iron particles, all right, we have 8 moles, you know, you have a little over 50 grams a mole, you have like about half a kilogram of iron here, half a kilogram. You could easily hold that in your hand. So that is a huge number, and yet you can hold it comfortably in your hand. That's how many atoms we have when we talk about a sample and why we need Avogadro's number. Okay, so let's do some more math, taking advantage of this new knowledge we have. And I'll talk about this visual flow chart I have up here for you guys who like visual learning. But we'll start here. How many moles of aluminum are in 25 grams of aluminum? So if you like this flow chart, we've been given 25 grams, which is a mass of aluminum. And we've been asked to convert to moles of aluminum. So you can see, to go from this box that has mass to the box that has moles, we would divide by molar mass. Now, I'm not going to give you this on an exam, but you could draw it real quick if you memorized it. And this is something visual learners might benefit from. Now, if you're just into dimensional analysis, I'll show you how the two reconcile. I would say I have 25 grams of aluminum, which was given in the problem, and I'm going to do some conversion to convert to the unit I've been asked for, which would be moles of aluminum. So what I need in this conversion factor, since it's in grams of aluminum, I need grams of aluminum down here to cancel out. What I need on the top is the unit I'm converting into, which would be moles of aluminum. So if I need the relationship between grams of an element and how many moles there are, well, I know that I'll have 1 mole of aluminum when I have this many grams of aluminum. And that's what the periodic table is good for. When you have 1 mole of aluminum, you'd have 26.982 grams of aluminum. So what I've done is, I said, all right, the problem told me I had 25 grams. For every 1 mole, I would have 26.982 grams. How many moles do I have? Or I start with mass, I divide by my molar mass to get moles. And again, molar mass is what you get from the periodic table. So 25 divided by 26.982, just a little under a mole, 0.927 moles of aluminum. Okay. Well, hopefully that math didn't seem too horrible. What if we're given moles and we have to work backwards to mass? Well, as you can see, we would take the number of moles and multiply by our molar mass. If you like that visual depiction. If you like dimensional analysis, I would say I was given 3.35 moles of copper, so moles of copper. I'm going to use some conversion factor and convert that to what I'm asked for, mass or grams. So it's asking me to solve for grams of copper. So what I need here is to have moles of copper on the bottom and grams of copper on the top. And so anytime you see grams and moles, whether it's like this, moles over grams or grams over moles, that is the relationship from the periodic table. So we find copper, which is right here, and you see that 63.546 grams per 1 mole. So I have 63.546 grams of copper when I have 1 mole of copper. So 63.546 grams. So 3.35 times the molar mass. And I get 213 grams of copper. All right. Now, of course, we talked about Avogadro's number, and the periodic table tells us if we have so many grams, how many moles we have. But the thing about moles is once we know that, we can use Avogadro's number to see how many total particles we have. By the way, this is the same number I gave you, just with one less sig fig. I said 6.022. This is only 3 sig figs. If you want more sig figs, you can look it up. All right. So if we're told that we have 5.25 moles of argon, we multiply it by Avogadro's number to get the total quantity of argon atoms. Or we can say 5.25 moles of argon, and we need to have atoms of argon is our answer. So if you like dimensional analysis, you would say, oh, moles of argon, okay. If I have 1 mole of anything, I would have 6.022 times 10 to the 23rd units of that thing. But in this case, I'd have 1 mole of argon, and I want to know how many argon atoms. So in any 1 mole of anything, we'd have this many particles, which in the case of argon would be atoms. So I multiply the moles times Avogadro's number. And I get a big number, 3.16 times 10 to the 24. All right. Any questions about that one? Okay, well, of course, then we're working backwards too. So if we tell you how many total particles they are, how many moles would there be? All right. Well, if we have the number, we divide by Avogadro's number to get moles. People like visual learning. Or I would say to myself, 2.33 times 10 to the 25th molecules of CO2. And we want to know moles. So I'd say, all right, I have 1 mole of anything when I have 6.022 times 10 to the 23rd of that thing. So 1 mole of CO2 molecules when I would have 6.022 times 10 to the 23 CO2 molecules. So how many moles would that be? Well, we'll do the math. And I get 38.7, and then this would be moles of CO2 molecules. So again, up here we talked about single atoms. Down here we talked about molecules of CO2, but again, we're just talking about the total number of particles, whether or not they're single atoms or whether or not they're groups of atoms as a molecule. All right. Now, yeah, sure.
Is molar mass mass number? Molar mass.
So the molar mass is a little different. When you say mass number, usually you're talking about a specific isotope, and you're talking about an atom, and then you would use AMU. When we're talking about larger quantities that we would use in calculations, we're going to use the molar mass, which is the average, a weighted average mass of all the isotopes. So it's it's the same concept, but the vocabulary word mass number has a slightly different nuance to it.
But for its amount, we consider mass number, right?
For what?
For molar mass.
For
We put
the molar mass, we use this number here.
this number.
Right, but you use the vocabulary word mass number, and I'm just trying to make sure that you understand it's a little different than molar mass. How the exact, so that's the only reason I'm splitting hairs, is I didn't know if that's what you were specifically asking. Okay, so now we have what appears to be similar questions, but they are slightly more complicated. So this question says, how many molecules of water are found in 135 grams? Obviously, 135 grams of water. So we say to ourselves, all right, we're given mass, and we have to go to number of molecules. Well, that's going to take 2 steps, because we can't go straight from mass to number unless you've already taken chemistry and you know some of the work you'd have to do. And if you've done that and can show your work, great. But for the rest of us who are just learning this, I'm going to suggest we take 2 steps. It's like a train. We started this station. We can't get to this station without stopping through the mole central station here. So we have to stop at each station. So we're going to have to go from mass to moles, and then from moles to number. Now, when we have water molecules, 135 grams, we would say, all right, I have 135 grams of water, and the first thing I need to do is convert that to moles. So before we would say, all right, that's no problem. I have 1 mole of water, and I'm converting out a grams of water, so I just need to figure out water's molar mass. You say, okay, that's awesome. So I look at my periodic table, and I'm like, oh no, there's no water on here, right? Water is H2O. But these are individual elements. I have a molecule that I need to figure out. So what do you think I need to do? Yeah, you got to add them up, right? Because the molecule's mass is the sum of the atom's masses. So I need 2 times 1.0079, that's the molar mass of hydrogen, plus 1 times 15.999, because I have 1 oxygen, 15.999, and 2 hydrogen. And I think you get, well, I'll do it. I don't want to try to remember it. 0.79 times 2 plus 15.9. Okay, so I get 18.015, because I can only go to the thousandth place, and that's grams per mole. Now, by the way, I've used the molar mass of water so many times. In the future, you'll just see me write 18.02, because I just have it memorized to 4 sig figs. All right, but anyway, this is how we would determine the molar mass if we didn't have it memorized. So now I know I need 18.015 grams of water to get a mole of water. So I write that down here. So I have 135 grams of water. How many moles is that? Well, if I divide by water's molar mass, I will know that. But I don't want to stop at number of moles. I need to know the number of particles. So I say to myself, okay, for every 1 mole of water I have, and I'm crossing this, have it in the denominator to cancel out with there, I have 6.022 times 10 to the 23rd water molecules. So I have my grams of water. How many moles of water is that? Okay, now I know, so I'm at moles. Now I know my moles. I multiply by Avogadro's number to get my total quantity. So it's a 2-step problem. So and hopefully you guys are checking my work. I got 4.51 times 10 to the 24th water molecules. Awesome. Okay. Now, what these next questions address is that you understand that water is H2O. We're going to visualize it later as an oxygen with two hydrogens connected to it. But you get the idea that this is a molecule that has three things that comprise it, two hydrogen and one oxygen. So it says, I need to fix this. This should be atoms. How many total atoms of hydrogen are in 135 grams of water? So we already did the work for 135 grams of water. The last question said that 135 grams of water is 4.51 times 10 to the 24th molecules of water, H2O molecules. So if we know that we have this many water molecules, and you can see that there's two hydrogen atoms per water, then you'd say, okay, if I had this many hydrogen molecules, I have two hydrogen atoms per one H2O molecule. So water molecules cancel out, and basically I just double my number of water molecules, and that's how many total hydrogen atoms there would be. So in my head, I would guess that'd be 9.02 times 10 to the 24th H atoms. So I just did that in my head. All right, now the next question says, all right, the same 135 grams of water, which we've established as 4.51 times 10 to the 24th water molecules, how many total atoms would there be? Well, that would ask you to look at the fact that water is 3 atoms per molecule. So if we have this many molecules, and we have 3 atoms per water molecule, we just multiply this number times 3 for the total number of atoms. So I got 1.35 times 10 to the 25th total atoms. So this is a good way to think about the parts and how math would apply to them. 135 grams of water, did the work, it's that many water molecules. Okay, if there's 2 hydrogens per water molecule, how many total hydrogens would there be? That many. If there's 3 total atoms per water molecule, how many total atoms would be in 135 grams of water? All right, question.
How do you graph the 2 and the 3 atoms? What's we have 2?
So water is made out of 3 atoms, 2 of which are hydrogen. So if we have this many water molecules, and within each water molecules, 2 of them are hydrogen, this is how many total hydrogens we'd have. Yeah, and then 3 here is because there's 3 atoms. So if we have 135 grams of water, the molecule represents them connected, and we have that many of those. If we ask how many total atoms comprise all those molecules, it would be that. Okay, now, again, more of the same, but there's a little subtlety to this. It's only a hard question if you miss the subtlety. What is the mass of 5 moles of chlorine gas? So you say, oh, to get from moles to mass, I just multiply by molar mass. So I say, okay, 5 moles of chlorine, and I'm showing you this as a bit of a trick, and then I need to have my grams of chlorine per moles of chlorine, which I'd look up on the periodic table. Does anyone see the problem so far? And it has to do with nomenclature and your knowledge of what chlorine gas should be. It's a diatomic molecule. So if we have chlorine gas, it is Cl2. So when we say 5 moles of chlorine gas, we're not talking about atoms of chlorine, we're talking about molecules of the diatomic gas. Now, why that's important? Because the grams for 1 mole of Cl2 will be twice what chlorine would have been. So here's chlorine, 35.453. So 35.453 times 2, I get 70.906 for Cl2, which is what we need. So that's what's tricky about it, is we need the mass of chlorine gas, which is diatomic. All right. Anyway, the answer would be 355 grams of Cl2. Yeah.
Would you get the same answer if you just divided the 5 moles in half and just kept it as just Cl?
Well, mathematically you would, but then you would be answering a different question.
Okay.
Yes. Okay. Now, you may remember, although it may seem like forever ago, that we started off this conversation by saying we used to talk about the mass of single atoms in atomic mass units, or single molecules in atomic mass units. But this chapter is different. So when we ask you what is the mass of a single atom of radon gas, we're asking it in grams. Because I know that you guys might, before this lecture, have looked at that and said, oh, radon. That's one of the ones that doesn't have a very specific mass number. It's just kind of approximated there at 222. But we can still use that. You might have said, oh, the answer is 222 AMU. And technically, you would have been right from 3 weeks ago. But it's not 3 weeks ago, so we want grams. All right, so if we have 1 mole of radon, we have 222 grams of radon. That's what the periodic table told us. But if we have 1 mole of radon, we also have 6.022 times 10 to the 23rd atoms of radon, because that's what a mole is. So if you have the same thing equaling 2 quantities, it's nice because you can solve for one of them. So what I'm looking for is the mass of a single atom of radon. So what I'm looking for is gram per atom. That's what my unit is going to be. So if these 2 quantities are the same, well, I can use them like a proof. So I have 222 grams of radon, and that same quantity will be 6.022 times 10 to the 23rd atoms of radon. So when I divide 222 by Avogadro's number, my units will be gram per singular atom. So let's try that. 222 divided by Avogadro's number. I get 3.69 times 10 to the negative 22. A very, very small mass for radon. Now, what I've shown you here is kind of like when if you've taken trigonometry or calculus, you're going to sit there and for the first 20 minutes of your math class, the teacher's going to do a proof and you sit there and watch and then say, okay, what's the bottom line? And then they tell you and you're like, all right, now I can start doing the problems. And the proof is just them showing you that what they're trying to prove is right is actually right. So this is my proof. Those of you who say, hey, I just want a simple way to answer the question, if you're asked for the mass of a single particle, you divide the molar mass by Avogadro's number. So that's what I did here. I took the molar mass of radon from the periodic table and I divided by Avogadro's number. So that's the bottom line. This is my proof. Okay. Well, looks like my thing got cut off here. All right. So, hopefully your guys' did your guys' print out okay? All right, so it's my printer then, not my graphic. Okay, so we are applying the mole concept to gases, and we're going to come up with a concept called molar volume. Now, there's a special set of conditions called STP. I'm sure STP is an acronym that other things use, like Stone Temple Pilots, if you're from the 90s. But anyway, STP in chemistry terms stands for Standard Temperature and pressure. So it's a set of conditions. Standard temperature is 0 degrees C, exactly 0 degrees C, or 273.15 Kelvin. But usually it's considered a Celsius temperature. Pressure is 1 atmosphere. Now, an atmosphere is a pressure unit we will talk about in several weeks from now when we talk about gas laws. But basically, this is about the pressure of the atmosphere weighing down at you at sea level. Or right about now, the pressure you're experiencing in this room is about 1 atmosphere. All right, so under these conditions, ideal gases behave in a very predictable fashion. Now, ideal gases, if you're wondering, are any Chem 305 gases. Now, you'll get into other classes and you'll see how gases can take on a whole math class unto themselves. But in Chem 305, in an introductory chemistry class, we're just going to assume that all gases behave in an ideal fashion, a very predictable, consistent way. So any Chem 305 gas is an ideal gas, and at conditions of standard temperature and pressure, STP, the relationship is this between moles and volume. 1 mole of any gas, 1 mole of any gas will equal 22.4 liters in volume. Now, I should underline gas too, because this doesn't have anything to do with liquids, just gases. But if you have a mole of particles of any gas at STP will occupy 22.4 liters, regardless of the identity of the gas. So our conversion factors for molar volume are 1 mole is 22.4 liters, or 22.4 liters per 1 mole. So those are the factors we're going to use for our gas law calculations. So you can imagine what's on the horizon. Molar volume practice. So these are the types of questions you would get. If you had 3.75 moles of any ideal gas or any gas in Chem 305, how much volume would it take up? How big would that gas cloud be under STP conditions? So these are all at STP. So we would say 3.75 moles of any gas occupy 22.4 liters per mole. So if we have 3.75 moles and each mole is 22.4 liters, we can figure out what it would be. So 22.4 liters at 3.75 moles, 84 liters. So we need 3 sig figs, so 84.0 liters. All right, hopefully that's not any worse than anything else I've thrown at you today. But what if you're given liters? We were solving liters, but what if I gave you liters and you had to work backwards and solve for moles? Well, that's all right. You'd say, okay, 125 liters. Well, I know that I will have 1 mole for every 22.4 liters of any gas that I have. So you'd say, all right, if I had 125 liters at 22.4 liters per mole, I'd have 5.58 moles. And this is of CO2, but only because it specifically said carbon dioxide. All right. Now, you may not believe this, but I would expect anyone in this classroom to be able to solve this problem in under 5 seconds. Does anyone want to do it in under 5 seconds? Besides me? Okay, that's just mostly to prove my point, because you're like, wait a minute, I'm supposed to do something and I can't, and then you're like, wait a minute, I should know this. Well, that's my point right here, is that this said, how many moles of carbon dioxide are in 125 liters? This question says, how many moles of argon are in 125 liters? But the take-home message is, it doesn't matter what the identity of the gas is, all gases, right? Any Chem 305 gas, it doesn't matter the identity at all. So you know what's true for carbon dioxide is going to be true for argon. 125 liters, this would be 5.58 moles of argon because, and this is where you want to write that note to yourself, the identity of the gas doesn't matter, just the quantity. So it's the same volume will have the same quantity. Same quantity has the same volume. Okay, well that one was easy. Now this next one has an extra step. So we saved a step here, we get an extra step here. How many grams of xenon are contained in 454 milliliters? Well, notice our conversion here specifically has liters. So milliliters are no good to us. So not to spend much time talking about the metric system again, but I have to divide by 1,000 to convert that to liters. So this is actually 0.454 liters. So I need units of liters before I can use my molar volume. All right, so I have 0.454 liters I've determined, and I have in 1 mole of xenon 22.4 liters. All right, so this solves for moles of xenon, but I'm asked for how many grams of xenon. Well, I didn't leave that much room, so let me just go ahead and solve for the moles. 0.454 divided by 22.4. According to my calculator, I would have 0.020268 moles of xenon. All right, but I need grams of xenon. The relationship between grams and moles is always here on the periodic table, so 131.29. So this is how many moles of xenon I have. I have 131.29 grams for every mole of xenon. And now I can solve for my grams of xenon. So that would equal what's in my calculator times the molar mass. And I get 2.66 grams of xenon. All right.